Generally, equations in aerodynamics were defined in the second chapter of Fundamentals of Aerodynamics in the previous course. But okay, this is not a problem at all. I think very useful from time to time to remember the equations, to remember the physical meaning. And now we will try to understand why actually in the differential form of the conservation equations we have a density outside of the substantial derivative and what is going on in this case. I hope you can see my screen. I will try to make a kind of a whiteboard and to explain you this question. Well, to remember what are we talking about, I would like to give you first definition of the substantial derivative, just to remember because we already studied before. So the substantial derivative by itself is denoted as d, for example, of some parameter, which we can see here in this example will be substantial derivative of the u velocity component, is defined as a sum of time derivative, for example, the partial derivative of the u component of the velocity by time, plus the velocity multiplied by the divergence of this parameter which we are calculating of the velocity, u component of the velocity. So this is the general form definition of the substantial derivative. We can write it the same way for any other parameter, for example, for the density, for pressure, for other parameters we might find, and this is a way. So we have this parameter in both parts on the left and the right part of the definition of the substantial derivative. Substantial derivative by itself is explaining for us how the flow properties of a moving fluid are changing. For example, we have some fluid element and it travels by some path from one position to another position. It's the same element, but it changes its geometry because of compression, and it can deform because of some rotational movement, right? We have to remember what is rotational and irrotational fluid. So the fluid element is the same, but while it's traveling from one coordinate to another coordinate, its properties are being changed, not only from one space position to another space position, but also with the time. So the substantial derivative for us is a form to explain how the flow properties are changing inside this fluid element. In this case, we are talking about the u component of the velocity and its variation with the space, which is happening here, okay, in this part, and what is happening with the time. So this is the first concept we must remember. The second concept we have to remember about two forms of the flow equations. There are flow equations in its integral form, right, where all the conservation laws are written as integrals. Integral by volume, integral by surface area, and they are all inside the equation, right, for mass conservation, for momentum, and for energy conservation. And there is so-called differential form of the conservation law, which is saying to us how flow properties are changing in infinitely small quantities, in infinitely small volumes, for example. These forms are used to express, to explain behavior of the flow in, for example, case of numerical simulation, when we are trying to solve this equation in differential form. The simplest equation is the following, is the continuity equation, if you remember, is saying the following, that the partial derivative of the density by time plus the divergence of product density by velocity would be equal to 0. Okay, so this is saying to us that change of some mass or density inside the infinitely small volume in time will be equal to the flow of this mass through the surface of this volume. This is simply saying this mass does not appear from anywhere and does not go to anywhere. It's always exists, and if our system is completely closed, the quantity of mass is the same. It's basically this. There are several forms of this equation, but now we will talk about this particular form because we are interested to understand how we go from this form of equations to substantial form of the equations. So your questions was, as I understood, if I understood correctly, was the following. We have to understand why in all the equations with substantial derivative, we have density outside of the derivatives, like density and then substantial derivative of the u component of the velocity by time, like this. And inside energy equation is something of similar, right? So this was the question, why we are having this density outside of the derivative if we have actually the density in general for compressible flow a function of coordinates and a function of time. So density is actually a function, a scalar function of 4 parameters, changing with the coordinates and changing with time. So let's go to see why density is actually outside of the relation of the derivatives. To understand this, we must first of all write the equation of momentum where this separation is happening. I will write you this equation in a classical divergent form. It will be partial derivative of the product of velocity and density by time plus the divergence of density, velocity, u component, and velocity. And then would be right part of the equation, which for us will be not so important for now, for today, but I will try to just write the pressure part, partial derivative of pressure by x, plus something. This something is related to viscous forces, viscous loads, moments, and same we have for the energy equation. We always have the sources of viscous energies or forces. Now we are not interested in this viscous part, so I keep it not filled because our goal is different for today. So I have this equation as the classical form, divergent form of the momentum equation, and I will try to convert it to the substantial derivative form. First of all, to make it, I will remember for you that there are two forms of differential equation, which I already say you the first one, right, is the divergent form. And the second one is the non-divergent form of the differential equation. How it can be transformed, any function, divergent function to non-divergent function, is the following. If we have a partial derivative of two parameters, which are functions, function A and B, product of these two functions, for example, by time, can be written in non-divergent form as A multiplied by partial derivative of B by time plus B partial derivative of A by time. It's well-known formula for you from mathematical analysis, and it's quite common formula, right? The difference between left side is that it's called divergent form, where from a physical point of view, when we are working with the physical equations, all the conservation laws are strictly satisfied. While we are rewriting this to non-divergent form like this, from physical point of view, not strictly follow with conservation laws. This can be the source of this. I will not explain right now. It can be read in the book which I upload in our Aprender recently, computational fluid dynamics and heat transfer, where is explained the difference between divergent and not divergent form of the differential equation and why actually is not satisfied strictly the conservation law. So I will not go this. I will just say for us that the left side of the equation is equivalent to the right side of the equation, but from mathematical point of view, but from the physical point of view, is not always satisfies the conservation conditions or conservation law. So this is the tool which we will use to split our momentum equation, which we have written before, this one. So this equation, I will split using my formula, and I will write the following way. I will split the first part, this first part of the derivative. I will write that, okay, let's start from the density, as we are looking for the density, right? Density multiplied by the velocity derivative by time. We are always talking about partial derivative, plus velocity multiplied by the partial derivative of density by time, plus this is the first derivative we wrote, and then we will same way we will split the right part. If you remember the divergence, this nabla function is also going according to the same rule of splitting derivatives. I will make you here one small annotation just to remember how it can be done. So I will write that divergence of product of two functions a, b will be found in its non-divergent form as a divergence of b plus b divergence of a. Same way as we did for the product of two functions and the partial derivative of this product. Same way. So I will write this second part of the momentum equation in this form. I will split here velocity and density velocity product. So basically what I will do, I will use the properties of my whiteboard, and I will write here some additional, I will just switch parameters. I will write here velocity and I will write here density. Since inside the brackets we have parameters, just the product is not important in which order they are written, right? So, and I will put additional brackets here. Okay. In this way, I will write my divergence function in the following way. I will write that is okay, velocity is going outside, right? And then will be divergence of density velocity product plus density velocity multiplied by the divergence of the u component of the velocity. Okay, this is the second part. I will mark by my black color. This second part is this, and the first part, the first derivative, is this one. Okay, and the right part of the equation is, of course, it stays absolutely same, and we will just keep it just to have an equation, a form of equation, minus dp by dx plus something. Now we will combine pieces with the density outside and combine pieces with the velocity, u component of the velocity outside. So basically what I will do, I will see that with the density I have this part, with the density I have this part, so I will combine them together, and with okay, with the velocity I have this part and this part. I will put velocity outside of the brackets there. Okay, let's see what we have. We have density. Inside the brackets we will have du by dt plus the second part is v, divergence of the velocity. Okay, and the second I make with the u component of the velocity. Inside the brackets we have the partial derivative of density by time plus, and then right part is the same. I just keep it writing to complete the right part of the equation. Okay, this is it. This one is identical to this one. And this is our continuity equation. This is our continuity equation, which says that left part is equal to the right part, and on the right part we see clearly it's equal to 0. So we go here and we may write that this is exactly equal to 0, right? So we cancel this part. And what we see here on the first part of the equation is that is a strict definition of the substantial derivative definition, which we have here. This definition, which we wrote at the very beginning, is absolutely the same. We write density substantial derivative by time, and here we have 0, then equal to minus dp by dx, and plus viscous forces, viscous moments, and body forces and other things. So this is the explanation actually why we have density outside inside this formula, basically because it's a simple mathematical procedure. Again, I would like to tell you that this mathematical procedure is not so strict with respect to the physical process which is happening. So mathematically, we can do this transformation. Physically, when we are looking to this equation, now we understand that maybe we have to take into account that not all conservation will be strictly respected. This is it. This is it. Same thing we may find also in the energy equation. I will not explain to you because it's absolutely same process, step by step, how to transform energy equation from its divergent to non-divergent form, and then how to calculate. And density will be always outside because we can take it outside of the brackets, transforming from divergent, from derivative of product to sum of products. This is it. I think we have some question. I will just take a look. Just a moment. I will take a look. Okay. You are welcome. Derek has started the meeting, right? Just for yourself, I hope, because the recording of the meeting is my responsibility, and I'm recording and I will publish the answer. So please do not publish anywhere. You can just use for your personal means. Okay. So this is the answer for the first part of the question. Why I changed the order actually, because the second question was about the total conditions. And I would like to explain to you in details. This question is super important question. Total conditions are widely used in all gas dynamics. And Without this definition, we cannot use any analytical simple model or simple calculation of gas dynamics properties. So what's the meaning? What's the sense of total condition or stagnation condition or full properties? You may find in the literature several definitions, several words which actually mean the same thing. So it's total conditions. Okay. It can be full conditions. It can be stagnation conditions. Stagnation conditions. All these three things are absolutely same things, but in a different books and different publications, you may find these three things, right? What is this? Is a process, is the flow process, can be explained mathematically in the different ways. For example, we have some flow which going in different directions, but this flow, let's assume it's the most simple case is isentropic flow, which is already adiabatic, so no losses in the flow, no heat transfer. At some moment, the flow is meeting the wall. Okay, the wall. What happens with the flow in this case? At some point, velocity will be equal to 0. In this case, all the flow properties will change, of course, will change because we know that there is a so-called quantity of the kinetic energy, right? There is a potential energy, there is a total energy, which is sum of these two energies. In the case of stopped velocity or stagnation conditions, all the kinetic energy of the flow is being transformed to potential energy of the flow. Let's take a look in the simplest case when our flow is inviscid, when our flow is incompressible. For example, density is equal to constant value. And in this case, we can easily use very well-known for you equation of Bernoulli, which is saying to us that if we have station 1 and station 2, that we can write the relation between station 1 and station 2 in the following way, that density velocity in square divided by 2, which is the analog of kinetic energy of the flow in the first station, plus pressure in the first station, which is analog of potential energy of the flow, would be equal to density velocity 2 in square divided by 2 plus P2. In this case, when we have completely stopped flow in the point 2, we have this part equal to 0, right? And since left side of the equation is equal to the right side of the equation, we see that pressure 2 is bigger than pressure 1. More the velocity we had before at point 1, more rise of pressure we have. This is a consequence from the Bernoulli equation, very well known, which you studied before in fluid mechanics, for example, or other disciplines. So this, in this case, it's very simple to receive the stagnation properties, right? We have pressure, so stagnation parameters are called having the 0 underscore here, P0, okay, is equal to P2. If we know everything from the left side of the equation, we knew what was the density, velocity, pressure. P2 can be calculated quite easily in this case. Temperature can be also calculated, or is given as an option, or calculated, for example, by the equation of state, where we have just to remember UP, density, gas constant, temperature. From here we can get the temperature. Okay, if I give the subscript 0 everywhere, under pressure, under temperature. We get from this equation temperature quite easily, and we calculate the stagnation temperature and stagnation pressure. Of course, the stagnation velocity is equal to 0. It's obvious. Always stagnation velocity is equal to 0. So this is the simplest case when you have Bernoulli equation. So there is no problem at all to calculate stagnation properties. When we have compressible flow and the density is not constant, Bernoulli equation by itself is not the only parameter not the only equation we must take into account. Why it happens? Because when we have not constant density, start to work other physical laws, right? Not just the energy conservation, but also momentum conservation and mass conservation. And in this case, we must see the continuity equation, we must see the momentum equation, and we must see the energy equation. From the continuity equation, I remember we have two parameters. We have density, right, which we just saw in the previous example, and we have velocity. Depending on the number of physical dimensions, we can have just one component of the velocity, or two components of the velocity, or if we have three-dimensional flow, we have three components of the velocity. And we have just one equation, so we cannot solve. We need for this another equations. For inside the momentum equation, we have also present density, u component of the velocity, v component of the velocity, w component of the velocity. And to remember for you that momentum equation is not just the one equation, but the number of momentum equations is equal to number of physical dimensions. For example, for three-dimensional flow, there are three momentum equations. So we have three more equations, for example, but we still cannot solve because there is a pressure entering inside momentum equation. So we need one more equation, and for this we have energy equation. Inside energy equation, we have also same parameters if you look carefully to the energy equation, but also start to have different parameters. For example, the energy by itself, definition of the energy, or internal energy, or enthalpy. There are several forms of energy equations which we will study very soon, and we can discuss separately these equations. And to solve one more parameter which is not matching with the number of parameters is not matching with the number of the equations, we find we need two more equations, which is equation of state, which I just wrote to you, this one, and probably the enthalpy definition, which is enthalpy equal to Cp multiplied by T, or internal energy equation, which is also similar, Cv multiplied by T. Depending on the form of the energy equation, we need one or the other equation or other things. Sometimes also there are other forms of the energy equation which do not involve enthalpy, but they involve entropy, for example. Okay, so what we do with the definition of stagnation properties for compressible flow, we need to solve this set of equations. We need to solve this set of equations. Since we have a number of equations, we have number of unknown parameters equal to the number of equations. These equations can be solved. And actually, it's one of the next topics we will study. I hope you will prepare, you will read at home this topic called forms of energy equations, where actually these equations are solved, and you may find very simple analytical formulas, very simple analytical solution of these flow equations, which are being transformed from differential equations to algebraic equations. Another comments I can give you about the stagnation properties are the following: that there are different types of flows, as we might see from the book. They are non-adiabatic flows. I'm talking about equation figure 7.4. Non-adiabatic flow, adiabatic flow, non-isentropic, and isentropic flow. For each of these types of flows, we have different flow processes. For example, adiabatic flow means that we have no heat transfer, right? It means that the temperature will not, or stagnation temperature in our case, will not change and will stay constant. Yes, will be constant. So parameter defined as T0 at one point in space, while the flow is going from one point to another point in space and with the time changing, T0 will be same, will not change if the flow is adiabatic. If there is no losses of temperature, we see no losses of stagnation temperature. Same thing we can talk about, for example, asentropic flow. Inside asentropic flow, when our quantity of entropy in the system is staying constant, is, for example, no boundary layer, no shock waves. These two cases. There are other cases I think we may find. Also, flow is asentropic, theoretically can be calculated, and flow moving from one point in space having some constant or some value of stagnation pressure, flow goes by its trajectory, we meet it in the other point, and stagnation pressure is the same because there are no losses in the flow. So stagnation pressure stays the same. If we mix adiabatic with isentropic, and isentropic is more simpler for us, of course, flow, we may state that both parameters, stagnation temperature and stagnation pressure, will be constant through the flow. And it gives us a lot of opportunities when we are going to see our forms of the energy equation. For the next time, I expect your questions about forms of the energy equations. What does it mean? Once calculated, for example, at initial plane or initial section 1, stagnation properties of temperature and pressure, if the flow is isentropic, this stagnation and temperature and pressure keep same value inside all the flow, everywhere. So we always may know if our flow will be stopped suddenly, what pressure it will have and what temperature it will have if the flow will be stopped suddenly at some point. How the flow can be stopped? For example, flow goes around the airfoil. Oh, I think it's a bit rotated. Okay, it's not very convenient for me to write in the tool I'm using here. Okay, the airfoil, and as you remember, we simulated, right? Here there is a leading edge. Near the leading edge, flow can be stopped suddenly. So we have stagnation properties, stagnation point, and also at the trailing edge, also according to the Kuta condition, we may find zero velocity or equal velocity on the upper and bottom side, or zero value of the velocity, which we clearly could see when we simulate the flow inside the ANSYS fluid. So this is very useful concept from the practical point of view, from calculation point of view. Very nice to know stagnation conditions, basically because in 90–95% of all calculations, flow is asentropic, actually is asentropic. And once calculated stagnation properties, they can be used in many forms of energy equation and can be calculated other parameters basing on these stagnation properties. Just to open some doors for you while you are reading paragraph or chapter about forms of energy equation, I can tell you that just using definition of temperature, stagnation temperature, and pressure, we can calculate the velocity at any arbitrary point we want. Velocity components in general and velocity vector, we can calculate the Mach number at any arbitrary point we want. We can calculate also the density and pressure at any arbitrary point we want, just having assumption of isentropic flow and previously calculated stagnation conditions. So we basically can calculate any flow property if we know stagnation properties, and this is a very powerful tool. So this is to motivate you about stagnation conditions, and I hope it's clear. If something is not still clear, please write questions in the chat. I'm ready to answer right now about stagnation conditions. And I will tell you that the definition of stagnation conditions is used not just in aero and gas dynamics. You will go further, many of you will go to propulsion, aerospace, aeronautic propulsion, where stagnation properties are super important and widely used to calculate the thermodynamic cycles, to calculate the performance of jet engines, of any type of aerospace engines. The stagnation parameters are one of the most important parameters, and one of the first questions which will be asked by professor is what is stagnation property and how can be calculated stagnation property. So about what is stagnation property we discussed today, discussed it already, and about how to calculate the stagnation property, I expect your questions in the chat, and if it's not clear how to calculate, we will discuss again, because it's a very long talk. Usually takes one complete lecture, just to give you an idea how to calculate stagnation property. Try to read the book. If will be not clear, I'm ready to help. If will be clear, just ask if you want some more details. And I think this is the end of my answer for the question about the stagnation properties. So very useful, very important, especially for the adiabatic isentropic flow. And we use this concept a lot in gas dynamics to calculate all other flow properties. It's not possible to give you all information at one piece, because chapter 7 is not short and not simple to understand right now. So now, today, my goal was to give you the physical principle, what is the stagnation conditions, the physical idea, right, the process. Next time, of course, we can talk about formulas, how to calculate inside the compressible flow. It's very important, I agree. But I think for today is quite enough to understand that is flow which is stopping, right? And because velocity is decreasing, the kinetic energy is going to zero, so potential energy is rising. Okay, density and the total pressure constant. No, of course not. If we go to, let me see, chapter 7, page 537, inside the Anderson, we can see four different cases. So these four cases are in general not adiabatic flow when we have all changing, right? What is not adiabatic, non-adiabatic flow is the flow where we have heat transfer, or we have chemical process, or we have source of energy, or some addition of the work, some addition of the energy on the system. Is not a non-adiabatic process. I mean addition, thermal addition. So in this case, we cannot say that stagnation pressure and temperature will be constant. Not, of course. It's the most complex, most difficult type of flow when we have non-adiabatic. And non-adiabatic flow is a very difficult by itself because there are many physical processes, right? You need to see what is the heat transfer, is it laminar or turbulent, what is the chemical source, for example, how the chemistry is going. So you need to involve many additional models. This is why non-adiabatic flow is very hard to calculate. And usually there are absolutely no analytical model. So this case, we are not discussing here because there is no analytical model. When we are going to non-adiabatic flow, it's just two possible ways to solve the problem. Or experimentally, you do real experiment, or inside aerodynamic tube, or inside some test bench. And second option is a numerical simulation of complete Navier-Stokes equation with all additional sources like boundary layer, turbulence model, chemical process, etc. Right. So non-adiabatic model we are not considering as analytical solution. Absolutely not. And then non-isentropic. Non-isentropic is also right when the entropy is not changing is quite hard to understand which not to understand, quite hard to complete all the model, all the mathematical model, and usually it's also impossible to do analytical calculation. But when we are going to adiabatic, it's already much simpler. In adiabatic, we have adiabatic law, right, from thermodynamics, probably you remember. Then is a very powerful tool to calculate relation between thermodynamic properties in the gas, helps a lot. And since adiabatic flow is saying to us that stagnation temperature is constant, our flow models simplify a lot and possible to have analytical solution. And the most simple, as I told you, is isentropic uh, isentropic flow. Isentropic flow where not just adiabatic, right, but also reversible process is possible, where the entropy is constant. And in this isentropic process, we have all. Constant pressure, stagnation pressure, and stagnation temperature. Like this. And this isentropic model is our main subject to study in analytical gas dynamics. So all the questions, further questions, which we will talk, calculation of the flow in the nozzle, for example, or low velocity flow, subsonic flow around the airfoil is isentropic flow. There are some models of non-isentropic flow which we also will study is shock wave. It's a normal shock wave or oblique shock wave is the chapter 7. Very nice analytical model of models of non-isentropic flows can be solved analytically. But for this, just for these two cases, for simple, very simple geometry of body and very simple geometry of the shock wave. And in general, not isentropic flow is also very complicated, very complex, as you will see in your simulation, because normal and oblique shock wave will be solved by you analytically, right, in work 1 and numerically in work 2. Okay. No, of course, from another point of view, I see a possibility to answer you that stagnation conditions always can happen, right? Stagnation conditions are basically when the flow stops. Flow can stop in any condition. It can be isentropic, not isentropic, adiabatic, non-adiabatic. Of course, stagnation conditions will happen or may happen, but not always we can calculate these stagnation conditions analytically. We can calculate them only in the very simplified cases, like isentropic, for example, or adiabatic case. For some cases, non-isentropic, but very few, as I told you, just the shock waves and simple geometry of shock waves give us possibility to calculate stagnation properties. Non-adiabatic flow is outside of our analytical possibilities. At least I did not see a nice model, and you will never find in the Anderson or classical aerodynamics analytical modeling of non-adiabatic flows. It's impossible. So from point of view of do they exist? Yes, of course. Stagnation conditions always exist because flow can stop in any point. And I think that to stop flow is much more simpler than to accelerate flow. To stop flow, you just need a wall perpendicular to the flow, and at one point it will stop. And to accelerate flow, you need to put a lot of effort, and to increase its velocity is a big work, because only increasing the velocity of the flow, for example, in the nozzle, we get thrust. If we cannot increase the flow, we do not get thrust. I hope I answered your question about existence and if they are constant or not. So I still reference you to take a look on page 537, where all these types of flows are explained, and probably they are very well explained, right? If you need more explanations, we can talk as well. So let me know if it's clear after you read the book. After you read the book, we still have a lot of time to spend discussing chapter 7. Let me see. I think we have at least 1 week, right, to finish chapter 7. So we have time to talk about it. Okay, people. See you then on Tuesday, our normal class, and we talk about other things. I will try to post these answers as soon as I can. And then have a nice weekend. Okay? Bye.